Welcome to the Introduction on Cryptography Concepts, brought to you by NowSecure. In this course, we will cover weak cryptography with a mobile context, protocols to avoid outdated cryptographic practices, techniques to test for weak or insecure cryptography, and finally, recommendations for secure cryptography such as key derivation functions. Let's get started. Let's begin with an introduction to crypto concepts. The mobile AppSec community uses cryptography to keep private things confidential. We also use cryptography to increase the trust in a world of a broken internet. To 1, gain integrity by proving that data is reliable and untampered. And 2, to gain authenticity by proving you are not speaking with an imposter. There's a daunting challenge, though. Don't assume all encryption is good. Plenty of security incidents have occurred because engineers used a great encryption technique, but the wrong use case. Unlike the web, mobile apps often store data locally. A criminal could gain physical access to the device and use it to decipher ways to undo your encryption, whether it protects data at rest or in transit. The mobile platform is like a mini internet, containing a variety of different apps, each living and breathing in a containerized world. Consequently, there's more to this than just securing data between the mobile device and a back-end server. We also need to look at securing communication between these mobile apps and the data we store locally within each. Centuries ago, generals like Julius Caesar needed to be able to share their strategy with the troops. But messages often got intercepted, leading to losses on the battlefield. To overcome this challenge, Caesar and his generals would each carry a set of 2 rotating disks to help encrypt and decrypt their messages. In the most common usage, they would rotate the disks so that every letter of the original text would be shifted 3 places to the left. So the letter S would translate to P, because S comes after R, which comes after Q, which comes after P. Now you try it. The letter E would be. If you said B, you got it. A simple shift, but very effective during those early days, because nobody outside of Caesar's trusted men knew how many rotations they had to make, and in what direction, to uncover the original message. Encryption takes something readable, or plain text, and transforms it into something that is not readable, also known as ciphertext. Sometimes it's necessary to share a secret. The receiver can use this secret to undo the encryption to recover the original message. Let's use our Caesar cipher as an example. Julius would have started with their secret message and used the Caesar disk as an encryption algorithm. The secret would have been to rotate the disk 3 letters to the left, which resulted in a scrambled message that his enemies couldn't decipher. Decryption would undo the process by turning encrypted ciphertext into readable text again. Now you try. Assume that the ciphertext is EF, and the secret algorithm to decrypt it is to shift each letter 3 letters to the right. What is the original plaintext message? EFGH. So the decrypted text would be E becomes H and F becomes I, which results in the word hi. However, a random output needs random input. How can we possibly get something random if we don't have something random to begin with? Apply the same function against the same input and you should end up with the same result, unless you have a random variable. Criminal syndicates have used the timing of slot machines to predict and outwit casinos for many decades. For example, in 2014, a group from St. Petersburg built a mobile app that would vibrate to indicate the best time to pull a slot machine and maximize winnings. After seeing heavy losses, investigators eventually cornered the group in 2017 and pressed charges. Slot machines weren't random enough. Casinos intended to skew seemingly random behavior in their favor, but criminals soon figured out their skewing and abused it to their advantage. Let's say you want something truly unpredictable. How would you go about doing it? In nature, entropy is non-deterministic. For example, thermal noise and quantum phenomena. But it's difficult to build mobile devices that source such random seismic events in nature. Instead, the operating system might consume heuristics on the mobile phone, like power usage or network patterns that appear to be random. We call these pseudo-random number generators. If we control the seed that powers an encryption algorithm, whether that be a secret password, a key, or other seemingly random number, then we can predict the output and break the encryption layer. Encryption can be applied to plain text in one of two ways. With stream ciphers, you would start off by creating a key stream. This key stream would have the same length as your original plain text. The stream cipher would then apply the key stream to the plain text using an X or command to encrypt it. A key attribute of a stream cipher is that the length of the encrypted output is the same as the length of the original plain text, message, or data that you want to encrypt. The transformation varies with time. Encryption can also be applied with block ciphers, which take a different approach. Block ciphers break the original message or data into blocks of bytes. Then, using the encryption routine, apply it to each block to form a block of encrypted text. Here, the first block applies to all the other blocks, then concatenates blocks of ciphertext together. There's a challenge, though. The original text cannot be perfectly divided into an equal number of blocks. For that reason, a block cipher will often apply some padding to fit and encrypt the entire message into the number of blocks. Now that we've covered the difference between block ciphers and stream ciphers, let's look at two dominant approaches to encryption. First is symmetric. Think of symmetric encryption as having a key to a door, whether it's a door to your house, office, or car. You would use exactly the same key to both lock and unlock that door. There's a challenge, though. How do we safely share that key with others? The problem with symmetric key encryption is that you need to share the same key with everyone. But how do you share this secret key? Over SMS, email, or phone? The challenge is that people can penetrate your communications, get that key, and render your encryption null and void. Public key encryption, or asymmetric encryption, solves for this weakness by introducing two different keys. Consider our analogy of a door. Unlike symmetric key encryption, which uses the same key to both lock and unlock the door, asymmetric or public key encryption introduces two separate keys and keyholes on the door. You would insert a lock key into the first keyhole, which would lock the door. You cannot use that same public key to unlock it, though. That first key and keyhole can only lock the door. To unlock the door, you need to use a completely separate and second key. You must insert this separate key into a second keyhole to unlock the door. But there's another challenge here. What if your unlock or private key is lost or compromised. Algorithms like RSA can be abused to encroach privacy. There are plenty of cases where a government demands to get a copy of a company's unlock or private key, like the recent online safety bill in the UK. Diffie-Hellman, a secure method of exchanging cryptographic keys over a public channel, uses a concept called forward secrecy. Instead of relying on a single private key, every customer on your platform gets a unique and separate lock and unlock key. As an added benefit, these keys are not stored anywhere, meaning if communication breaks down, nobody can recover the keys to decrypt the original traffic, not even the sender or receiver. To summarize, symmetric key encryption uses the same key to lock and unlock the door. Symmetric key encryption is efficient, but how do you safely share that key with others? Assume that a key you've shared is lost or compromised. The adversary can also decrypt your traffic. Public key encryption mitigates the threat of stolen keys by introducing two different keys. If somebody steals the public key, it's okay. They cannot decrypt other people's data. Why? Because you only, the keeper of the private key, can unlock the door to view shared data. You might ask, why don't we just use public key encryption since it's safer? Well, because it's slow. Public key encryption is a lot slower than symmetric. However, we can combine these two cryptographic schemes, symmetric key encryption, which is more vulnerable to stolen keys, although very fast, with public key encryption, which mitigates against key theft, but is much slower, to form trust in a public key infrastructure. Hashing is a one-way form of cryptography. The idea is that you shouldn't be able to recover the original text just by looking at the hashed value. It's irreversible. For example, in a court case, you can use a cryptographic hash to prove the cyber evidence you collected is untampered. That hash legally proves that the data wasn't tampered with or modified. One hashing algorithm called MD5 was once a very popular hashing algorithm. But it was vulnerable to hash collisions, meaning that different text can have the same hash value. These hash collisions weaken our confidence in the integrity of the hashing algorithm that proves the data was not manipulated. Hashing is a great way to prove that data wasn't tampered with in a court of law. We can use the same concept for other use cases. For example, how does a government validate a passport? They would likely use a watermark and apply hieroglyphics on the passport for a stamp of integrity and authenticity. Later, when you provide your passport, they would look at it again to confirm that it is a valid passport issued by the government. So a MAC, Message Authentication Code, or an HMAC, a message authentication code using a hash function, would do something similar. You would take your data, work out a message authentication code, and package the two in a MAC data structure. The data is pushed through a MAC algorithm to produce the message authentication code. There are two kinds of message authentication codes. Think back to our earlier discussion on being random. If you apply this same function on the same data, you will always get the same output. 2 to the power of x would always be the same value. 2 to a power of 2 equals 4. 2 to a power of 3 equals 8. For encryption to be random, we need a random factor as part of its computation. Therefore, when it comes to MAC or HMAC values, we would use a secret key as part of the calculation. This key is circulated amongst all the parties. To reference the passport analogy, The key in that case would be the watermark or the hieroglyphics on the passport itself. We share those indicators, not with only ourselves, but with other governments on how they can prove this is a valid passport issued by us. The challenge is, even though we know that this message wasn't tampered with, given the secret key, how do we know that this is actually issued by the sender, and not by someone else who knows or has the secret key? That's where digital signatures come in. Continuing the analogy of passports, how can a government validate a passport and authenticate you as an individual? They would capture a photo of you or your signature on the passport. The border control agent verifies that the photo and the signature match your identity. Therefore, HMAC or MAC prove integrity and improves authenticity, but it does not prove non-repudiation, meaning it does not unequivocally prove you are who you claim to be. Digital signatures built on HMAC by adding that proof. First, provide the data to get a hash value. Then, use a private key to sign the message. Remember, always keep private keys to yourself. A public key can be shared. Only you would have the private key. Only you have your face. Only you have your signature. This is your private key. You apply your face to a photo and your signature on the passport. A government would then prove that the passport is authentic, but they will also use your photo and your signature to prove that you are who you claim to be. In other words, they would use your public key to verify that again, recover the hash value that proves this message wasn't compromised. These functions can now be combined. Starting on the left, we see that encryption needs to be random, so we need a pseudo-random generator. For that to happen, we need some seed. We would generate the seed over a random number, and we call that a salt value. The salt value is ingested into a key derivation function, or KDF. The key derivation function would use something random, in this case the salt value, together with something you know, the passport, to generate a master key. The master key in this case can then be ingested as an input to another key derivation function to produce a data protection key. This data protection key can then be used as an input to encryption. In summary, hashing functions, MAC, and digital signatures can be combined to form more intricate solutions to complex problems. The key takeaway is that cryptography has many moving parts and lots of different building blocks. It's on us to know which component to use for each use case and how to combine these differing components to solve a specific problem.